Welcome to this continuation class on electrical conduction in ceramics. We have had earlier two classes on the preliminary discussion on the electrical phenomena and the different theories to explain the conductivity behavior of different solids. We will continue that discussion in this class as well. This is the so called Bragg diffraction, the relationship or the formula for Bragg diffraction, n lambda equal to 2d sin theta, and for theta equal to 90 degree n lambda equal to 2d, okay. And k equal to k is the wave vector again, n lambda d sin theta. Now, we were discussing, or this concept of Bragg diffraction came in because of the consideration of band model of solids to explain the electrical behavior in particular, or the phenomena of electrons, the behavior of the electrons within the solid. And we have considered in a periodic lattice in which the electrons are moving in a periodic lattice, not on a constant potential, but on a periodic potential. And because of this periodicity, this Bragg diffraction, the concept of Bragg diffraction also came in, because whenever there is a periodic lattice, any electromagnetic wave passing through that periodic lattice, there is a chance, there are chances of diffraction, and because of the periodicity there will be a constructive interference. And if the angle of impedance, angle of incidence is about 90 degrees, then there will be a complete reflection back, which means basically the electrons impinging on such kind of a surfaces having this d spacing, and theta of course is 90 degree. So, with this d spacing, the lambda will be completely, or the wave particular ray will be completely reflected back, it will not pass through. So, there will be some kind of a forbidden barrier to this kind of movement of the electrons, and that comes from the periodic lattice. And these are the relationship lambda critical, that at what particular lambda value this will be satisfied, that will be 2d d, there is set of values 2d d and 2d by 3, and when that will be converted to the k value, the critical value k in the k space value or the wave vectors, then this will be plus minus d, plus minus 2d, plus minus pi by d, 2 pi by d and 3 pi by d. Now, this will be clear when we go to the next picture or next figure. What exactly, this is what exactly is the consequence of the so called periodic lattice, followed by the chronic body model and the Bloch theorem. Combined all these, what we finally come up with is the same kind of Ek curve what we have observed in the free electron theory, the parabolic curve, and that is our original Ek curve, parabolic Ek curve, which we have earlier drawn and seen and explained. Same thing happens here also, but with some difference. The difference is there is certain amount of discontinuity. There is certain amount of discontinuities here. This curve is not continuous. Earlier we have seen these are discrete points, but almost a quasi continuous line. These points are discrete points, energy levels, discrete energy levels, but otherwise it is a quasi continuous line. But because of the periodic potential of the lattice and the consideration of Bragg diffraction what we have just discussed, there is certain amount of discontinuity happens, and these discontinuities do not happen anywhere. Discontinuities occur at those values of k. Okay. These critical k values which you have given here is pi by plus minus pi by d, plus minus 2 pi by d and plus minus 3 pi by d. That kind of particular specific values of k, we have this discontinuity, and you can see towards, of course, one can find out through some mathematical calculation that there is slight amount of bend in those discontinuities. These are different specific values, critical values of k, where there is some amount of discontinuity. That means any the earlier you have introduced the concept of any, that is the density of states. The density of states do change at those points, at those discontinuities or critical values of k, and as a result the Ek curve bend little bit downwards here, and here it bends towards upwards. Okay. So, considering that there is a discontinuity from this to this, suddenly the if we go on changing the k value, then the energy here changes almost on a continuous manner, and then suddenly there is a discontinuity there. So, it does not follow the original path of the E versus k curve, but there are certain discontinuities. That means, here the energy levels are not available. Okay. So, if the electron is having this energy level, then from this energy level the next energy level, if it acquires certain energy, it will go, it has to acquire this amount of energy and go to the next level. It cannot stay within this energy levels. So, these energy levels becomes forbidden energy levels. Okay. So, this is where it comes from the Bragg's reflection, the electrons gets reflected from there. So, it cannot stay or it cannot occupy any energy level between these values, because this is your E energy axis. So, from this energy level it has to jump to this energy level, it has to go to the next energy level. The next energy level here, these are forbidden energy levels. So, at different levels, different points of the k vector, different values of the k vector, such discontinuities occur. Okay. So, this is one set of discontinuity minus pi by d and plus pi by d. So, one can say this up to this is one volume of the Ek curve, where there is a continuity of the energy levels. Then there is a gap from this one to that, and it starts from the next level there. Okay. So, if you draw this horizontal lines here, then it starts from there again and it ends in the lower level. It ends there and then suddenly it goes to the higher level and it starts again. So, once again there is a continuous energy levels available from this band. Okay. So, this band of energies are continuous. Then again there is a discontinuity, and once again there is a continuous band. So, the energy levels are really not continuous, or whatever we have seen in free electron theory. Free electron theory provides the energy levels are continuous energy levels, okay, whereas in reality the energy levels are really not continuous, it is discontinuous. So, it comes in the form of bands of energy levels, and that is the reason the particular name, the band model, comes in. So, we have bands of energies, and in between the bands there are forbidden energy levels or band gaps. So, this is the main consequence or the main outcome of the band model of solids, and we will see later on that this band model can explain many properties and the behavior of different groups of metals or groups of solids having different ranges of electrical properties, whether it is conductivity or resistivity. So, finally, the outcome is more important for us, because we do not need to go to the details of the mathematical calculations, but ultimately this is our outcome. The outcome is the main outcome, and that has to be remembered all the time. This is our main outcome, that the EK curve is not a continuous curve, does not have a continuous energy levels or energy states available to the electrons. The electrons can have either within the continuous bands, but not in the band gaps. So, it cannot stay. So, either it stays in the lower band or on the higher band, but not in between the band gaps. So, that is a very important consequence of the band model, and one can, this is of course, we have drawn it as two dimensional figure. It is, as I said earlier, these curves are actually 3 dimensional, and you have a 3 dimensional volume which contains large number of points of different discrete energy levels. So, these are actually different volumes, although it has been taken as a cross section. So, but these are actually volumes. So, this is one volume which contains the continuous or semi-continuous, quasi-continuous energy levels. Then there is another volume, a band. In this case, here is a band, but actually a slice of volume, and then there is another. Okay. So, of course, the pictures are very simplified here. They are neither slice nor the surfaces are plane. So, most of these cases, because this is completely related to the crystallographic directions crystallographic planes. So, the k values actually relates to the crystallographic planes in the reciprocal lattice, particularly in the reciprocal lattice, and from that one can see that the slices what you see here is actually not a plane cylindrical surfaces, but basically it is a complex 3 dimensional figures, and these regions of where the continuous or semi-continuous or quasi-continuous energy levels are available, these are called zones, and a particular name has also been given to these zones. These are called Brillouin zones. Okay. So, the first level, for example, in this picture, the first level of continuous energy levels is called the first Brillouin zone, and then this is the second Brillouin zone and the third Brillouin zone, and so on. It is difficult little bit to visualize the exact shape of these zones, but basically there is it is a 3 dimensional cuboid kind of pictures, and it depends on what kind of crystallography relationship it has. So, but the Brillouin zones are nothing but these bands. Okay. In the whatever you seeing in the 2 dimensional is the bands, these are actually called the Brillouin zones. Now, there is a consequence of these complexity of these geometric figures. These bands or these band gaps, these energy levels are not really uniform throughout in different directions or different in the different axes. Okay. So, although in a particular section we found that they are quite symmetrical, but they are really not symmetrical. The surfaces are quite complex and not a plane surface at all. So, this is our original expression of the free electron model, okay, E equal to h square k square by 8 pi square m. On that it has been superimposed. Okay. So, it is there is a lot of similarity so far as the EK curve is concerned between the free electron theory and the band model, with the exception that there is a discontinuities, and these discontinuities explains many of the different properties which we encounter in reality. With this we define what is a band gap, because this band gap is of extreme importance to us to understand the behavior of different solids, including ceramic materials, which we will discuss later. So, the band gap is actually the minimum gap considering all directions of motion is called the forbidden gap or the band gap. Okay. Here we are introduced the so called direction of motions, right. That means a particular crystallographic direction in which the electrons are moving. For our mathematical calculation, we have taken a reciprocal lattice. The k vector is actually reciprocal lattice, but actually it has a correlation with the actual real lattice. Okay. So, the electrons are moving in different directions, crystallographic directions. At different points in the direction, the electrons encounter different energy levels. So, although these are the two different spaces, one is the volume space, the another is the energy space. Okay. So, they have some kind of a correspondence between them. So, when the electrons resides in a particular volume space or the actual real crystallographic site, it also has certain energy level associated with it. Okay. So, that is the, although in the energy space we get band gaps, but in the volume space there is absolutely no discontinuities, but the energy wise they have discontinuities, and some of the energy level or some of the energy states are forbidden energy states. So, it can stay cannot stay in everywhere in the crystal. We will explain exactly what this means so far as the considering all the directions of motion, right. We will take it up in a few minutes, next slide maybe. If the maximum of the lower band, we have different levels of bands, the first Brillouin zone, second Brillouin zone and the third Brillouin zone. So, there are different levels and the energies are different. So, when one Brillouin zone ends, another Brillouin zone starts after with a gap of certain energy levels. So, that is what it means here. If the maximum of the lower band or for one direction of motion is higher than the minimum of the upper band for the same or any other direction of motion, there is no forbidden gap. This is called overlapping band. Now, if we go back to this diagram, we see that there is a discontinuity here. So, if we draw this vertical horizontal line and this horizontal line, there all through there is a discontinuity, but it may not be so. It may not be so. This may not be an horizontal line at all. It may be a complex line. Okay. It may be a complex line like this or something like that. Of course, not in curved surfaces, because it has certain geometry. So, it is basically a combination of different planes. So, if we take any particular, let us say any vertical direction, although or a large number of vertical directions, then although we are finding a gap here, but if we draw a line there, there may not be any gap. There may not be any gap on that particular axis. Okay. So, it not necessarily that all through this gap exists. It may or it may not. So, if there is no gap or there is some kind of an overlapping in a particular direction, but there are gaps in other direction, in that case also we can say that there is no gap, or there is a bands are getting overlapped with each other. Okay. So, we will look into such kind of situations at later stage. So, that is what in that context you have to read this paragraph. If the maximum of the lower band for one direction of the motion is higher than the minimum of the upper band for the same or any other direction of motion, there is no forbidden gap. This is called overlapping band. Such a situation happens if the potential energy of the electron is not a strong function of the position of the crystal. We have already considered a periodic lattice, and depending on the crystal, depending on the particular lattice, the variation may be less or more. So, if the variation is more, then such situation forbidden energy gap the overlapping bands may not occur, but if the variations are very strong, then the forbidden energy the overlapping may not occur. So, such a situation, that means overlapping bands happens if the potential energy of the electron is not a strong function of the position in the crystal. Okay. So, it depends on what is the variation, what is it a very strong variation, it is a very drastic variation, or a very shallow variation. Depending on that, we can expect we may or may not expect a overlapping band. We are talking about band gaps, and the band gaps are very, very important. Now, this is what we call a direct band gap. That means, this is the particular direction on a this is the direction, one can say this is the direction of the motion. The electron is moving from a lower energy to a higher energy along this direction, and the bands across this direction, the lower band is like this, okay, which means it is not a flat at all, as we have visualized there, we might have visualized there, but the surface of that band is not a flat band or a flat surface, it may be a completely curved surface, quite complex curved surfaces. Okay. And so, this is a continuous energy band, these are the continuous energies are possible here, whereas this is discontinuous, that means these are these are forbidden energy levels, all these are forbidden energy levels, including this small gap. Okay. So, along this direction the gap is more, as you go from this to the right or the left, the gap is increasing, but the minimum gap may be somewhere here. Okay. So, the minimum gap is somewhere here, and when we talk about define about the band gap or forbidden energy levels, we will talk always about the minimum gap. Okay. These are the two different surfaces. This is in fact the one Brillouin zone, this is another Brillouin zone. So, the gap is between this and along the vertical line, or one can electron can move in the in an inclined way also. Okay. So, it can move start there and go in an inclined follow an inclined path as well, but generally the vertical direction is here been shown, and the minimum gap is the forbidden energy gap. Always we have to remember this is the minimum energy gap. So, if you have to, if a particular solid has two different Brillouin zones of this nature and we have to say what is the band gap, then we have to draw this gap. In fact, later on we will see that we do not draw this surfaces as curved surfaces, we always draw as plane surfaces or a parallel lines, but that is only schematic, that is not a real situation, that is only a schematic situation, and it is only for a particular direction of motion. Okay. Although we give a width to it, but the width does not have any significance there. we will see that. So, this is the direct band gap, that means along a particular crystallographic direction the minimum occurs here. Okay. So, this is the maximum of the lower band and the minimum of the upper band is on the same direction, on the same crystallographic direction, then in the it is called the direct band gap. However, a situation may happen that a situation like this, the maximum of the lower band occurs in one direction with a k vector here, whereas the minimum of the upper band occurs as a different k vector. Okay. So, there is a gap, there is a distance between this k value and this k value, where this is there is no such distance, two k values do not exist, the single k value has the maximum and the minimum, whereas here the maximum is for one k value and the minimum is for another k value. So, this is what we call the indirect band gap, although the band gap here it is not this, neither this. Okay. Band gap is the minimum distance, minimum gap between the maximum of this and the minimum of this, that is always the characteristics band gap of this material, whereas this is direct band gap and this is the characteristics band gap, and we draw normally if we have to draw a band diagram of this solid, we will draw a line there like this horizontal line and we will draw another horizontal line here. Okay. So, that will represent the band gap for this material. Here also we have just drawn two horizontal lines, one is this one and there is this one and this is the band gap. So, we do not draw a curved, okay, and we are not concerned what is the band gap away from their maxima or minima. This gap may be larger, but we are not concerned about that, because the transfer, the electron transfer will take place along this direction, the minimum gap direction. So, this is the concept of what we call a direct band gap and indirect band gap. These are very important when you are talking about any electronic devices, some contacts and so on. Band gap has a very important role in designing microelectronic circuits or microelectronic devices or semiconductor devices. So, band gap is one of the most important or utilized concept for designing of different semiconductor devices, including the microelectronics of different kinds, the lasers, semiconductor lasers. There are many devices requires the concept or the knowledge of band gap. Yeah, this is what I was talking about, the valency and conduction bands. And as you can see here, we have drawn a horizontal line, a very simplified diagram, extremely simplified diagram, and in fact, in reality never such horizontal gaps exist, okay, like this. In fact, you also remember here that there is no axis here. Whenever we draw a band diagram, we never give a horizontal axis. What is the horizontal axis? It is immaterial in fact. In fact, we are talking about only the gap here. Okay. The horizontal axis does not have any significance here. So, in fact, this gap is along a particular vertical line. Since drawing a vertical line with a gap is not a very convenient or very good way of drawing something. So, for better representation we draw a horizontal line, okay, but the width is absolutely immaterial here in any way. So, this is how we draw a band diagram. This is one band diagram, one band for continuous band. This is another continuous band of energy levels, and in between you have band gaps, which is called the forbidden energy gap. and no electron can reside on any of these energy levels here, okay, any of the energy levels particularly energy levels are forbidden for that particular system or particular solid. Anyway, with that we also should define what is the valence band and conduction band. These are the two terms which we extensively use whenever we talk about electronic conduction in semiconductors particularly, or even in metals and insulators. Okay. So, ultimately it is the valency band and the conduction band, the concept of valency band and conduction band are most important. The definition of valency band is the highest occupied band is designated as the valency band. Now, once again maybe we have to go back to that original picture, this one. We say this is one band, the lowest band, lower energy band, and then higher energy bands, and then it continues almost indefinitely depending on the number of the structure of the solid and the number of available electrons in that solid, free electrons of course. Now, there are one band here or one gap here and one gap here. So, we have to understand which one is more important to us or which one actually controls. All of them do not control the property, mostly one of them control the most of the properties, and that depends on how many number of electrons are available, free electrons are available in that system, and how many bands are available. So, normally the lower the number, the first the lower band will be occupied, and then if the number of electrons is more than the number of energy states available here, then it will go to the next band. That is how it is getting filled up. So, in that context the band gap or the band diagram when you normally draw, either we have to draw this one and this one is the lower band and this one is the upper band, or we can draw this one as the lower band and that one is the upper band. So, for any particular solid there is a band gap. Now, band gap normally refers to the highest gap or the highest energy gap in the for that particular system. So, what we are saying here that the highest occupied band is designated as the valency band. So, this is the valency band, and below that whatever energy levels are available, including if there is a band gap, does not matter, but all the energy levels are filled up below this level, then this will be called the valency band. Okay. So, and the next higher band is known as the conduction band. So, the next higher band will be the conduction band. So, we are mostly concerned with these two bands all the time. This is your valency band and conduction band. In any kind of literature, any kind of discussion, you will always find that there is a mention about the valency band and the conduction band. So, we are mentioning here these two bands. In that context, once again going back to the earlier curve, in some material we will see this may be the this is the valency band and that is the conduction band. In some other material one can see that this may be the valency band and above that there will be conduction band. So, it depends on the particular specific material, but we are more concerned about the gap. What is the gap? What is the energy gap available, and that controls the property of the material to a large extent. So, this is the valency band and conduction band definition, and there are also some nomenclature here. For example, EV, the top of the energy level of the valency band is designated as EV, E subscript V, whether top of the or bottom of the conduction band, the energy associated with that or energy corresponding to that is designated as EC, and the gap is always E gap. Here it is written E gap, but mostly it is EG, E subscript G is the designation of the band gap. So, E gap or EG is actually nothing but EC to EV. Okay. Many a times what happens, this, because we do not know, if we are drawing this particular diagram, we do not know where is our reference, where is zero level. Okay. It is not necessary to know, to be known actually, because most cases we take this as the reference, this as the 0 level, and then onwards or upwards becomes our axis. So, reference most of the time reference is here. So, EV becomes your reference, so that EC becomes EG. Okay. So, the gap is our concern, and it is relative to a particular energy level. Normally the top of the valency band is taken as the reference or 0 level. Well, with this we come to another very important issue now. So far we have discussed the charge species is basically electron. In semiconductor physics, we have something different. Metals, when you are talking about metals, electron is the basic species, which is the conducting species or the charge transport species. But when we talk about band gaps, then there are another concept comes in, the concept of holes. The holes are generated in the valency band due to excitation of the electrons from the valency band to the conduction band, or acceptance to the electrons from the conduction band by the acceptor ions. So, holes are generated in the valency band due to excitation of the electrons from the valency band to the conduction band. Okay. So, this is our valency band and this is our conduction band. Okay. So, the valency band is occupied, all these are the black dots are actually represent the electrons. So, the electrons are available at different energy levels. Okay. Once again there are the horizontal axis does not mean anything, basically it is the vertical axis which is of our concern. Horizontal axis only gives us the kind of volume or the total number of electrons on that particular energy level. So, from the conduction band by the valency band to the conduction band, or acceptance of the electron from the conduction band by the acceptor ions whose energy levels are just above the valency band. Okay. Sometimes we will come to that later, but before that, let us say there is an occupied levels, the electrons are here, okay, and this is the forbidden energy gap or band gap, the EG. No electron can reside in this white region, because these energy levels are forbidden. The electrons cannot accept these energy levels. So, it has to accept sufficient energy so that it crosses over, jumps over to the next band, that is the conduction band. So, this is our conduction band, this is the pink one is the conduction band and the black one is the valency band. This is filled up with the electrons, and once some thermal energy, for example, some thermal energy is provided to it, these electrons accept this thermal energy, gets energized. So, the energy content increases and goes to the next level in the conduction band. Now, once this electron goes to the conduction band, all these electrons has actually got excited from the valency band to the conduction band, and consequently there are some vacant sites. So, these circles are actually the vacant sites of the electrons, which originally were supposed to be there, but because they have been excited by additional energy from external sources, so they have left behind certain vacant sites. So, these are actually electron holes, these are called the electron holes. So, it is basically a vacant sites left over by the electrons which have been excited to the conduction band. So, it is basically a vacancy of electrons. So, that is the concept of the electron holes. The reason why they are important is they can also act as a species, charged species like electrons, because once this hole or the hole is created or the site is vacant, so it becomes a positively charged species. So, it becomes a positively charged species. So, this hole becomes a positively charged species, and these holes can move just like the electron under the application of the electric field. Just like a vacancy can move because of the concentration gradient, here because of the potential gradient or the external applied field, these holes can move in the particular direction, in the direction of the field in fact, and the movement is very simple, because if this electron jumps over to the next hole, then hole actually moves there. So, the hole moves in the opposite direction than that of the hole, that of the electrons. So, they are actually equivalent within this array of electrons. If the electron moves in one direction, the holes automatically moves in the other direction or the reverse direction. So, either we can concentrate on the movement of the electrons, or it is better to, in this case, to concentrate on the movement of the holes, because holes are normally less in number. So, you can concentrate on the movement of the holes rather than the movement of the electrons, particularly when the number of holes are much less compared to the available number of electrons. The reverse is true when the number of electrons are less and the vacant spaces are more. That happens when it is in the conduction band. So, for our purpose, we will see the less number of electrons have been jumped over to the conduction band. So, this is the conduction band. It was originally empty, let us say at lower temperature or close to absolute 0. These sites, that means the energy sites are available, but they are not occupied by the electrons. All the electrons were at the valency band, right. Now, with increasing temperature, maybe that is one of the ways to excite. There are other ways to excite also. So, providing thermal energy, these electrons will have jumped over, and a relatively less number of electrons are jumped over, because these electrons will never jump over. It is the electrons which is closer to the energy gap here, or the highest energy, closer to the highest energy. One can say this was the Fermi energy, but it is not the Fermi energy. We will come to the concept of Fermi energy in this case in a different way. So, closer to the Fermi energy have jumped over to this. So, this less number of electrons are available here compared to the number of sites available, number of energy sites available. So, it is easier to put our attention on this. So, in this case we will not, there are vacant sites, in OVLE, that is not our consideration. Here we will look at what is happening to these electrons. So, these are conduction electrons. So, they are negatively charged. So, they are negatively charged. As soon as you apply an electric field, they will move to the slightly higher energy level, but not too high, not it will not go to that level, it will be almost kind of a horizontal level, slight increase, a very small increase in energy because of the application of the electric field, whereas if you change the temperature, then the energy input is much larger. In any case, so these are electronic charge carriers. So, our attention will be on this, whereas when we are talking about charge carriers here, although electrons are also moving in this, but our attention will not be on the electrons, it will be on the holes. So, we will say the holes are charge carrier here, okay. Positively charged holes or the vacancies of the electrons are the charge carriers, rather than saying that the electrons are charge carriers here. So, in the valency band, the holes will be the charge carriers, where with the positive charge, and here on the conduction band it is the electrons which will be the charge carriers with the negative charge. So, that is what is the concept of hole. So, any semiconducting surface where whenever there is a band gap and there is an excitation of the electrons from the valency band to the conduction band, holes will be created, and holes are almost equivalent to the electrons, except that they have a positive charge rather than a negative charge as in case of electrons. So, they can also have mobility, they can also be considered the concentration, hole concentration, electron concentration, electron mobility, hole mobility, and so on. So, holes are for all practical purposes a second variety of species which can transport charges in the system. The holes are generated as has been explained, and once again to read it out, holes are generated in the valency band due to excitation of electrons from the valency band to the conduction band, or there is another process by which the hole can also be generated. Here we have shown that the electrons are getting excited from the valency band to the conduction band. The holes can also be created, that means a vacancy can also be created in the valency band by if this electron does not move that far, but there is a local site available. Okay. Somewhere here, if there is an absorber or an acceptor of the electrons which has an electron affinity, that means it has a tendency to absorb electrons from any source, then for example, an ion, an impurity ion, okay, whose electron affinity is much larger than the host material. This is the band gap this is the energy diagram for the host material, in which we have added some impurity, and that impurity incidentally may have a very strong affinity for very strong affinity for the electrons. So, it has a tendency to absorb electrons, then that will absorb electrons from the valency band and also will create holes. So, corresponding electrons will not be created in the conduction band, but the holes will be created in the valency band. So, that is what is mentioned here, or acceptance of the electrons from the conduction band by the acceptor ions whose energy levels are just I am sorry, I think there is a mistake in the statement. For acceptance of the electrons from the not from the conduction band, it should be valency band, I am sorry. I am sorry. So, this is the valency band, because the holes will be created always in the valency band, okay, not in the conduction band. Conduction band will always give rise to electronic charge carriers or the electrons, free electrons. So, the acceptance of the electrons from the valency band by the acceptor ions whose energy levels are just above the valency band. So, this is the top of the valency band, and there if you have some ion in the solid, the same host material, that means mostly an impurity ion whose electron affinity is much larger than the host material, then it will accept some of the electrons from here to the next level. It will attract some electrons, and by that process also you will get some holes generated. So, there are two ways by which holes can be generated in the valency band. One is the electrons jumping over from the valency band to the conduction band because of thermal energy, conduction band of the same host material, or the electrons going to a foreign material whose energy levels is very close to the valency band. So, we can identify a element or an impurity whose energy level is somewhere there, and it has a great affinity for accepting electrons and get ionized by itself. By that process also it will take away some electrons from here, and in the process you will get holes, right, and corresponding electrons will not be available there, okay, because it is not a direct excitation, thermal excitation. It is by a different process the holes are generated, and those electrons are not available, will not be available for the conduction process. Okay. These electrons which are being transferred or excited from the valency band to the conduction band, they are available for electronic or the conduction process under the application of the electric field. But the electrons which are going to the acceptor level, they will not be available, they will be completely tightly bound by that particular atom or ion, and they will not be free for the movement under the application of electric field. So, that also have to be recognized that the two processes are slightly different. In one case you will the charge carriers will be same. Okay. So, whatever holes, number of holes will be created here, the same number of electrons will also be created there, and both of them will contribute to the current, both of them will contribute to the charge movement. Whereas, in other case only the holes will be available for charge carrier, but the electrons will be accepted or absorbed by the some other element, and that will not be available for charge carrying purposes. So, this is the concept of hole, and this concept of hole is very important for understanding the overall conductivity and the behavior of the conduction process. In that context, we must distinguish between two different types of semiconductors. So, one is intrinsic, the other is extrinsic semiconductor. Intrinsic semiconductor is where there is no impurity atoms. So, there is no acceptor atoms, or there is another form of impurity which is donor atoms. Sometimes the impurity level or the energy level of the impurity is very close to the just below the conduction band, in which case it will donate electrons, okay, and it will have a property of ionization, its ionization potential will be low. Okay. So, it will donate electrons to the conduction band. It will not create holes here, but it will donate electrons. So, by that process also it increases the charge carrier concentration. So, these are the two different processes. By adding certain impurities of two different kinds, one can either accept electrons which are called acceptors and create holes in the valency band. The another variety is donate electrons to the conduction band, and then of course, there is no question of hole there. So, corresponding hole will not be created because a second element has come in the process, and there is no hole created. So, such types, if there is no impurity atom present, the material is very pure, and whatever charge carrier concentration, charge carrier creation is concerned is all by thermal excitation. So, the same number of electrons and same number of holes will be created in the process, then it is called intrinsic semiconductor. Whereas, if you have some impurities, either it may be a acceptor ions or a donor ions, they will be called an extrinsic semiconductors. So, the impurity control semiconductors are called extrinsic semiconductor, whereas pure materials, or if there is no impurity ions available, then it is called intrinsic semiconductors. So, their behavior will be slightly different. And there are two different types of impurity ions. One is a donor type and there is a acceptor type. So, accordingly we have two different types of semiconductors, the N type semiconductor and P type semiconductor. When there are donor ions are available, that means the ions are donating electrons from the conduction band. So, the number of electrons or the number of charge carriers or the negative charge carriers is higher than the whole charge carrier. So, it becomes N type, it is negative type, whereas if you have an acceptor type impurity, then the number of holes are larger than the number of negatively charged electrons, and so it will be called a P type semiconductor. So, the predominance of holes as the charge carrier are there, that will be called P type semiconductors, and where there is acceptors. If the donors are there, then the negative charge are predominant. So, that will be N type semiconductor. So, both of them are very important from their point of view, and we will see how they are useful maybe in the next class. The time is up for the time being. So, thank you very much for your attention, and we will continue this discussion in the next class. Thank you once again.